Hello and welcome back. The last video I talked about conductance of electrolytic solutions, and in this video I'll be talking about the other type of electrochemical cell, that is electrolytic cells and electrolysis. So let's get started. In an electrolytic cell, external source of voltage is used to bring about a chemical reaction. So this is the difference between the galvanic cell and electrolytic cell. In galvanic cell, we saw that a spontaneous chemical reaction gives us voltage, but in electrolytic cells, it's the reverse. That is, you need to provide external source of voltage to bring about a chemical reaction. The electrochemical processes are of great importance in the laboratory and chemical industry. One of the simplest electrolytic cell consists of two copper strips dipped in an aqueous solution of copper sulfate. If a DC voltage is supplied to two electrodes, then Cu2 plus ions discharge at cathode, that is negatively charged. The following reaction takes place at cathode. Cu2 plus aqueous gains 2 electrons to give Cu. Some points note here is it is reduction again because copper 2 plus has gained 2 electrons and there is a reduction in oxidation number. The plus 2 has reduced to 0, so it is reduction again at cathode. In galvanic cell, cathode was positively charged, but in electrolytic cell, cathode is negatively charged. So it is better to remember that cathode is the place for reduction and anode is the place for oxidation, rather than remembering cathode is negatively charged in electrolytic cell, cathode is positively charged in galvanic cell. Instead of remembering the charge related to the cathode or anode, it's better to remember these two things. Cathode is for reduction and anode is for oxidation. It's the same for any cell. So, and you can get the charge from the equation. Yeah, so let's move on. So copper metal is deposited on cathode. At anode, copper is converted into Cu2 plus ions. So copper is positively charged in electrolytic cell. The following reaction takes place at anode. Copper gives Cu2 plus 2 electrons. Thus, copper is dissolved or oxidized at anode and deposited at cathode. So, anode oxidation again. Yeah, and please to remember this. This is the basis for an industrial process in which impure copper is converted into copper of high purity. The impure copper is made as anode that dissolves on passing current, and pure copper is deposited at cathode. Many metals like sodium, magnesium, aluminum, etc. are produced on large scale by electrochemical reduction of the respective cations where no suitable chemical reducing agents are available for this purpose. Sodium and magnesium metals are produced by electrolysis of the fused chlorides, and aluminum is produced by electrolysis of aluminum oxide in presence of cryolite. And this will be covered in detail in Unit 6 of Class 12. Now let's see quantitative aspects of electrolysis. Michael Faraday was the first scientist who described the quantitative aspects of electrolysis. Now, Faraday's law also flows from what has been discussed earlier. Now let's look at Faraday's law. After his extensive investigations on electrolysis of solutions and melts of electrolytes, Faraday published his results during 1833 to 34 in the form of following well-known Faraday's two laws of electrolysis, and it is simply called Faraday's first law and Faraday's second law. So what's Faraday's first law? It states that the amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to quantity of electricity passed through the electrolyte. I repeat, the amount of chemical reaction which occurs at an electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte. And that's the first law. And what is second law? It states that the amount of different substances liberated by the same quantity of electricity passing through the electrolytic solutions are proportional to the chemical equivalent weights, that is, atomic mass of metal divided by number of electrons required to reduce the cation. So these are two important laws given by Faraday, Faraday's first law and second law. Let's try to apply them now. There were no constant current sources available during Faraday's times. The general practice was to put a coulometer, that is a standard electrolytic cell, for determining the quantity of electricity passed from the amount of metal, generally silver or copper, deposited or consumed. However, coulometers are now obsolete. Even I haven't used this word much, so we don't see it nowadays. And we now have constant current sources I available, and the quantity of electricity Q passed is given by Q is equal to IT, where Q is in coulombs, I is in ampere, and T is in seconds. This is in fact the direct definition of current. In layman's term, it's rate of flow of charge. So I is equal to Q by T, and putting things around, we get Q is equal to IT. You have seen this in physics. The amount of electricity or charge required for oxidation or reduction depends on the stoichiometry of this electrode reaction. For example, in the reaction Ag plus electron giving Ag, 1 mole of electron is required for the reduction of 1 mole of silver ions. So 1 mole of silver ions require 1 mole of electron. We know that charge on 1 electron is equal to 1.6021 into 10 power minus 19 coulomb. Therefore, the charge on 1 mole of electron is equal to the Avogadro number Na times that charge 1.6021 into 10 power minus 19 coulomb, which comes out to be 96,487 coulomb mole inverse. Is this number familiar to you? Yes, this is Faraday's constant. And this quantity of electricity is called Faraday, and it is represented by the symbol F. For approximate calculations, we use 1F is equal to 96,500 coulomb mole inverse. Just to revise, where did we see this? We saw this in Nernst equation. We write E cell is equal to E naught cell minus RT by NF times ln Q. So that F and this F are same, 96,487 coulomb mole inverse. But for convenience, we write it as 96,500 coulomb mole inverse. So we have two reactions over there, and Mg2 plus 2 electrons giving Mg, and Al3 plus 3 electrons giving Al. So it is obvious that if we take 1 mole of Mg2 plus, we need 2 moles of electrons, and if we take 1 mole of Al3 plus, we need 3 moles of electrons. So you need 2F and 3F. What is F? F is Faraday. What is Faraday? Faraday is coulomb mole inverse. I'm sorry, 96,500 coulomb mole inverse. Yeah. So this charge passed through the electrolytic cell during electrolysis is equal to the product of current in amperes and time in seconds. Simply Q is equal to I times T. In commercial production of metals, current as high as 50,000 amperes are used. That is something like 0.518 Faraday per second. It's a huge number, right? So let's solve a quick question now, a simple one again. A solution of CuSO4 is electrolyzed for 10 minutes with a current of 1.5 amperes. What is the mass of copper deposited at cathode? So you can take 15 seconds from now, you can pause the video if you need more time, and then we will discuss the solutions together. Okay, let's discuss the solution now. We know that charge is equal to current times time, which is 1.5 amperes times 600 seconds, that is 900 coulombs. Don't forget to convert 10 minutes to seconds. So 10 minutes is 600 seconds. Don't forget that. So we have charge as 900 coulomb. Then according to the reaction, Cu2 plus 2 electrons give Cu. So we need 2 Faraday or 2 times 96,487 coulomb to deposit 1 mole or 63 grams of Cu. Why 63 grams? That's atomic mass of copper if you don't know. So if you need 1 mole of copper, you need 1 mole of, if you need 1 mole of copper, you need 2 moles of electrons. So we saw that 2 moles of electrons, the charge will be 2 Faraday, that is simply 2 times 96,487 coulomb. And yeah, I think the rest is clear. So for 900 coulomb, the mass of copper deposited is 63 gram mole inverse times 900 coulomb by 2 into 96,487 coulomb mole inverse. It's just like 63 grams give you 2 times 96,487 for 900 coulomb. What will you get? Just cross multiplication, and this will give you 0.2938 grams. So what is this 0.2938 grams? If you pass 1.5 ampere for 10 minutes to a solution of CuSO4, you get 0.2938 grams of copper deposited at cathode. Now let's study the products of electrolysis, which is quite interesting also. The products of electrolysis depend on the nature of material being electrolyzed and the type of electrodes being used. What are the two things? One is the nature of material being electrolyzed, the other one is the type of electrodes being used. If the electrode is inert, like platinum or gold, it does not participate in the chemical reaction and acts only as a source or sink for electrons. On the other hand, if the electrode is reactive, it participates in the electrode reaction. Thus, the products of electrolysis may be different for reactive and inert electrodes. The products of electrolysis depend on different oxidizing and reducing species present in electrolytic cell and the standard electrode potentials. Moreover, some of the electrochemical processes, although feasible, are so slow kinetically that at lower voltages these do not seem to take place, and extra potential, which is called overpotential, has to be applied, which makes such process more difficult to occur. Now let's look at some examples. If we use molten NaCl, the products of electrolysis are sodium metal and chlorine gas, as you expect. So here we have only one cation, that is Na+, which is reduced at cathode, Na++ electron giving Na, and one anion, Cl-, which is oxidized at anode, and Cl- gives half Cl, 2+ electron. During electrolysis of aqueous sodium chlorate solution, the products are NaOH, Cl2 and H2. In this case, besides Na+ and Cl- ions, we also have H+ and OH- ions along with solvent molecules H2O. So where are this H+ and OH- coming from? Water. So when we use aqueous sodium chloride, we have these extra 2 ions apart from Na+ and Cl-. So at cathode, there is competition between the following reduction reactions: Na++ electron giving Na and H+ plus electron giving half H2. So the standard electrode potential for the first one is minus 2.71. For the second one, it is 0.00 volt. Why 0.00? Because it's a standard hydrogen electrode. Yeah. The reaction with higher value of E0 is preferred at cathode. So the reaction at cathode during the electrolysis is H+ plus electron giving half H2, and it's not Na+, voila. But H+ aqueous is obtained by dissociation of H2O, that is H2O liquid gives H plus and OH minus ions. Therefore, the net reaction at cathode is H2O plus electron giving half H2 plus OH minus. So now let's look at anode. At anode, the following reactions are possible. One is Cl minus getting converted to half Cl2 plus electron, and the second one is 2H2O liquid giving O2 plus 4H plus 4 E minus. And the standard electrode potentials are 1.36 volt and 1.23 volts. And I say 1 and 2 for first one and second one. The reaction at anode with lower value of E0 is preferred. So what do we expect? We expect water should get oxidized in preference to Cl minus ions. But on account of over potential of oxygen, reaction 1 is preferred. So this is very important. Why is reaction 1 preferred? Because of over potential of oxygen. Okay. Thus, the net reactions may be summarized as NaCl aqueous in terms of H2O giving Na plus and Cl minus. That's a normal thing, and that's not the reaction we are looking for. So at cathode, we have H2O liquid plus electron giving half H2 plus OH minus. At anode, we have Cl minus giving half Cl2 plus electrons, and adding these two and multiplying terms, multiplying ones and twos if you need, you get a net reaction as NaCl plus H2O giving Na plus OH minus plus half H2 plus half Cl2. So, and Na plus OH minus is NaOH. So we have these three products over here. What are they? NaOH, H2 and Cl2. The standard electrode potentials are replaced by electrode potentials given by Nernst equation to take into account the concentration effects. During the electrolysis of sulfuric acid, the following processes are possible at anode. H2O getting converted to O2 plus 4H plus 4 electron minus. We have 2 moles of H2O by the way. And the standard electrode potential is 1.23 volt, that is 1. And 2 moles of SO4 2 minus, that is sulfate ions, getting converted to S2O8 2 minus ions plus 2 moles of electrons. And the E0 cell for this is 1.96 volt. So this is the second one possible. For dilute sulfuric acid, reaction 1 is preferred, but at higher concentrations of H2SO4, reaction 2 is preferred. Why? Write the Nernst equations, take into account the concentrations, and you will see why. That's an exercise to you. So with this, we have come to the end of this video. To summarize, we started our discussion with electrolytic cell. Then we saw quantitative aspects of electrolysis, where we studied about Faraday's first law and second law. And finally, we saw the products of electrolysis, and we saw two important reactions in that. One, we took molten NaCl, we analyzed the products, which were sodium metal and chlorine gas. Then we took aqueous sodium chloride and we analyzed what will be the products of electrolysis. And in the next video, I will be talking about batteries, fuel cells, and a common phenomena which you might have heard, that is corrosion. I hope the content in this video was clear, and I hope to see you in the next video. Goodbye.